Hello, welcome back, and today we're going to talk about an interesting topic, nuclear chemistry. And from the bomb, a lot of nuclear chemistry has to deal with nuclear weapons. So let me review back to the four fundamental forces, gravity, electrostatic, nuclear weak, nuclear strong. As I said before, chemistry is mostly about the electrostatic force. But we're going to talk today about nuclear chemistry, so we have to include the nuclear strong force. And nuclear strong force, this is what binds the nucleus together. For some nuclei, there are just too many positive charges. So the nucleus is got protons and neutrons. Neutrons have no charge, protons do. All these positive charges in the nucleus are repelling. So there has to be something to hold it together, and that's nuclear strong force. But for some nuclei, they are not particularly stable. We give that a special word. That's called radioactive. Radioactive nuclei means that they're unstable. And we'll talk about what makes them radioactive and what's not. So let's talk about nuclear chemistry. This deals with the nucleus. Usually we're talking about electrons transferring. Today we're just going to talk about the nucleus, the protons and neutrons. And applications besides atomic weapons are nuclear power plants, medical imaging, some sterilization for food, carbon dating, and smoke detectors. The ones you buy at the store are in fact radioactive. Different types of radiation. Let's start with alpha particles. Alpha, these are low energy, low penetration. So your skin being hit, if you have an alpha source, your skin will typically protect you. Alpha sources outside the body, like a smoke detector, not a real big deal. Alpha source inside of your body are actually very dangerous. So something like radon gas in your lungs is very dangerous. Beta particles, these are electrons. These have slightly more penetrating power. They're not that much of a danger. A couple examples, your eyes tend to be a little sensitive to beta radiation. But they typically get absorbed in the first couple layers of skin. Gamma can go right through you. Gamma, if there are enough gamma rays, there can be some big trouble. X-rays, so gamma rays, this deals with nuclear, the nucleus of the atom. X-rays have a little less energy than gamma rays, and you get X-rays by taking a metal and hitting it with an electron beam. So that's so a word of caution. Sometimes having lead as a radiation shield, X-rays, lead will stop X-rays, but if you have beta electrons coming off of something and you put lead on someone, you will actually generate X-rays, which is probably worse than the beta electrons. So that's how they make them in the dentist office. You have an electron beam shooting at a block of metal, and then that will give off. Then as the electrons hit the metal, it will give off X-rays. And these are also harmful ionizing radiation. So how far do things penetrate? Alpha particles, paper, your skin will block them. Beta particles need to have a little sheet of aluminum. Gamma rays need a foot of lead or a couple meters of concrete, so they're a little bit harder to block. And half-life, so maybe you've heard half-life before. This is how long it takes for half of whatever isotope you have to disappear. And this is a characteristic value, so you can tell what it is by its half-life. So for instance, iodine-131, they use this for thyroid imaging. Also, it's a byproduct of nuclear fission. Iodine-131 has a half-life of about 8 days. That means after 8 days, you have half the sample. After 16, you have a quarter, and so on and so forth. And that's why the iodine-131 from the Fukushima nuclear event had decayed so quickly, because of the short half-life. And so what happens after 4 half-lives? So it's a half times each one, so there's only 1/16 left after 4 half-lives. So what do we use radioactivity for? So we'll talk about medical soon, but non-medical, tracers for reaction pathways. We do this in chemical research. Put radioactive material on something and then see how it reacts and see where the radioactivity is. Also, tracers for material flow. You're like, why would you want to add radiation to something? Let's say that you have a petroleum oil pipeline like the one we have from up in Canada, or I guess that's natural gas too. We have a natural gas pipeline from Canada to the continental United States, and we have a leak in it somewhere. So how do we find the leak? Well, we put a little bit of radioactive material on there, we fly over with a helicopter and have the Geiger counter, and we've tracked the radiation, and when the Geiger counter stops going off, like, oh, I think the leak is here, so then we can find the leak much more quickly. Activation analysis, this is one way to figure out what's in stuff. If you take something and you hit it with slow neutrons, it will become radioactive, and then by the gamma rays coming off, you can figure out what's there. Also, for food preservation, if you hit things with gamma rays, this will make the food, will sterilize things in the food and help the food survive longer. So let's talk about the medical applications, and there's lots of medical applications. Carbon-11, this is used in, they put it in glucose. This is for brain scans, for PET scans. They put these in, one of the ways to scan your brain. For chromium-51, figure out blood volume. Why? For congestive heart failure. Someone has congestive heart failure, this is one way to do it. If someone's having trouble uptaking vitamin B12, you can use cobalt. And also cobalt for radiation, cancer, gallium for bone density. You can also use technetium-99 for that as well. Use gallium-67 for lungs, iodine-131 for imaging and treatment of thyroids, iridium-192 for breast cancer, iron-59, this is to see how anemic someone is, phosphorus-32 to find skin cancer and tumors in one's eyes, plutonium-238, they typically don't do this anymore. They typically use lithium-ion or lithium batteries for that. Not lithium-ion, I'm sorry, I misspoke, but plutonium-238. But they do have a plutonium-238 battery on the Voyager probes. Radium-226 for cancer, selenium for pancreas, sodium for obstructions in your blood flow, right? So that kind of like the tracers in the pipeline, same thing for our blood. Technetium-99, this is for bone scans. I've actually had one of these done. And thallium-201, treadmill stress test. Tritium to figure out how much water one has, and xenon, this is a gas for lungs. And this is a picture of a bone scan, and the idea is that for an injury, more blood's going to flow that area. And you can see the imaging of this person's kidneys. You can see something going on here in the person's elbow. That tells you there's probably an injury to his or her elbow. I think it looks like a male to me, actually. Then if you notice here, this is the person's bladder, so it's not that there's something going on right there in the individual's groin. It's just the body's flushing out the technetium. And you can see another zoom in of the person's kidneys there. And dating, so specifically carbon dating, we can date things by using isotopes. This can be typically used for living things, and it can do for geological things. So if you wonder where the age of the Earth, they say the Earth is 4.6 billion years, where did that come from? It comes from the ratio of uranium to lead, and also the amount of potassium-40 we have, and we'll talk about that later. So things that were living that are less than 50,000 years old, we can carbon date them, and carbon date them using carbon-14. Here's a general idea of carbon-14. So carbon-14 is made by hitting nitrogen with nitrogen it makes up most of the atmosphere, with a neutron from the sun and or other stars and cosmic rays, and it forms radioactive carbon-14. That reacts with oxygen to make radioactive carbon dioxide, and then this carbon dioxide, or this radioactive carbon, is then disappearing. But plants uptake carbon dioxide by photosynthesis. And so because of that, there's more or less the same amount of radioactive carbon in living creatures. Because some of it disappears, but then plants are photosynthesizing, animals are eating plants, animals are eating other animals. So pretty much every living creature on Earth has, on average, about the same amount of radioactive carbon. Now, when someone dies, if I die, I'm no longer going to eat. I'm not going to be... So that means as I die, my radioactive carbon is decaying, but it's not being replaced. Likewise, a plant, it stops photosynthesizing, it stopped going to replenish its radioactive carbon. And so by the level of radioactivity, you can figure out how old something is. There's a problem with that now. If someone tried to radiocarbon date us, it'd be a little different, because we've blown up 500 nuclear bombs in the atmosphere, over 2,000 if you include over underground. But because of those about 500 nuclear airborne tests, there's a little bit more radioactivity around than there has been in the past, so it wouldn't work for us. So this is what you can use, carbon-14 for dating of organic things, that were living. Organic also means carbon-containing, so anything that's carbon-containing that you can date. Tritium, you can use it for short-term. For aged wines, I mean, you're not going to do it for the cheap wine you get, at least not even the... I like wine, but I wouldn't buy wine that someone would age it with that. This is for a really expensive wine. Lead for skeletal remains. Potassium for rocks. Ruthenium for meteorites, and uranium for rocks. So you can see here the 4.6 billion year lifespan of the Earth comes from this right here. The potassium, 40, and uranium, specifically the ratio between uranium and lead. So chemical reactions we've covered. Let's talk about nuclear reactions. Nuclear reactions deal with the nucleus, and so in a nuclear reaction there will be a change in the element. And two types, fission and fusion. So fission is when things break apart. Fusion is when they come together. If you can't remember it, think of a bone fusion. That's when two bones come together to form one. So nuclear fusion is when two nuclei form a bigger one. And fission, that's how nuclear power plants work. Fusion, that's what runs stars like the sun. So here's fission. And it can work spontaneously, but typically what happens is a neutron is absorbed by the nucleus and it breaks the atom apart. And then this can generate what's called the nuclear chain reaction, where one breaks apart, which forms other, and other. And now, if this is done really quickly, an atomic bomb works off this principle. If this is done slow and controlled meaning these extra neutrons can be absorbed, that's how a nuclear reactor works. And where does this energy come from? I've been talking to you, drilling you in the conservation of matter, the conservation of energy. So how do we create energy out of nothing? Well, actually matter and energy are interchangeable by one of Einstein's famous equations, E equals mc squared, where E is energy, m is mass, and c is the speed of light. So 3 times 10 to the 8 squared, that's 9 times 10 to the 16. That's a big number. That's why a little bit of matter can turn into a lot of energy. Now, different nuclei have different amount of energy. So this y-axis here is the binding energy. That says how much energy is in the nucleus. Another way to look at it is up here, this is the most stable, and these are the unstable ones. And here, the x-axis, this is a nucleon number. This is a number of stuff in the nucleus. And hydrogen here is low, and by fusion it'll generate energy until you get to iron. Iron is the most stable nuclei, and then these become unstable. And so things so nuclear fusion will be exothermic, meaning giving off heat up to iron, and fission will be exothermic up to iron as well. And actually iron is what causes stars to explode, and we'll cover that later. So what do we use fission for? The first use, well, I guess before that we did generate heat from it, but atomic weapons. Atomic weapons, the atom bomb uses fission, and the first ones were used in warfare. Well, the only ones used in warfare were Nagasaki and Hiroshima. Nagasaki is a plutonium bomb. Hiroshima was a uranium bomb. And something to note, these are odd numbers. For nuclear fuel, you're going to have an odd number on the top and an even number on the bottom. The even numbers tend to be more stable, and the odd numbers, they can release something that's called the pairing energy. And what does fission do? It releases a lot of energy. A lot of energy. A little bit of matter turning energy releases a lot of energy. And so a bomb, it's suddenly, uncontrollably, and a reactor, it's slowly. And then these can cause neutrons, which can cause other problems. Here's a picture of the first atomic blast. Well, no, I'm sorry, it's not the first atomic blast, that's a tritium. This is the first one used in warfare. This is the one at Hiroshima. And here are the testing. So we've used more than just the two in in warfare. We've United States, we've led the charge. We've blown up about 1,030 nuclear weapons. Most of them are underground, but all in all, we've blown up about 500 in the atmosphere and about 1,550 or so underground or in the ocean. And hopefully no more will be exploded. And we use fission for peaceful purposes, like nuclear power plants. And so we get our electricity in America, about 1/5, about 20% of it comes from nuclear power. And then how nuclear power works, it's fission, and then the fission though is controlled by control rods, and then this absorbs neutrons to stop the progression of neutrons so it doesn't get out of the way. A nuclear power plant will never explode like a nuclear bomb, because they do not make it concentrated enough. There's only 3% or so nuclear fuel in a nuclear power plant, whereas an atomic bomb has almost pure nuclear fuel. So it's very, very powerful. But really, a nuclear power plant is just a heat engine. It just generates heat, and that heat is used to boil steam, which in turn drives the generator. So here is a nuclear power plant. This is the reactor core. These things are control rods. It generates heat, which then generates steam. And the way electricity is made, you make it by taking magnets and you spin it around a wire. The magnet spinning around the wire induces electricity in the wire. So these magnets going around the wire is what generates electricity, and that's what the turbines do. That's how electricity is generated. And this is what it looks like inside a nuclear power plant. This blue light, this is called Cherenkov radiation. That's what happens when beta particles, beta electrons, hit water. It glows kind of this eerie kind of blue color. If you ever see a movie like the K-19, The Widowmaker, you'll notice the water was blue. And that this is just a glass, it's not blue water. That blue water, when I saw that movie, I kind of shuddered, because those guys were not going to be doing well. So if you ever see water that looks like this, don't go swimming in it. So some problems with nuclear power, it's the waste. So nuclear power plant is going to generate something about the size of a compact car of nuclear waste, which is really radioactive, and it's really hot. Like, it's literally temperature-wise hot. And it takes about 5 years or so to cool down so it can be reused. But there are some wastes that can't be reused, like strontium-90 and cesium-137. These are relatively toxic. They take about 500 years to decompose. Problem is, steel container lasts about 50. So what do? In America right now, we keep it all, each nuclear power plant keeps its own waste. So we might put it in Yucca Mountain. That's one of the things we're looking at doing. Plutonium takes, 242 takes much longer to decompose, about 100,000 years. Now, nuclear accident. I'm not going to talk about 3 Mile Island or Fukushima, but I'm going to talk about Chernobyl. So 3 Mile Island, both Fukushima and 3 Mile Island, there was a meltdown, but the radiation was contained pretty well in 3 Mile Island. Fukushima, some of it was released in the atmosphere and some into the ocean, but the containment has held so far. and there is not as nearly as bad as Chernobyl. Chernobyl was a terrible accident, and Fukushima is not as bad as Chernobyl, no matter what they say in the news. And basically, there was a core meltdown in Chernobyl, and these people, a huge amount of radiation was released, and about 4,000 Ukrainians, called the liquidators, they all died, and there's been many other more disabled. So here's a picture of the reactor in Chernobyl, and you can see that the explosion was pretty massive. This is not like an atomic bomb. This explosion, just like the one in Fukushima, well, it's unlike, this is worse than the one in Fukushima. This is an explosion just from the expanding gas, not a nuclear blast. Here are the liquidators. Liquidators, these are the guys that came and cleaned up. They all died of acute radiation poisoning. What do we use fusion for? Hydrogen bombs. So there's atom bombs, that's the fission bombs, plain old nuclear bombs. Hydrogen bombs or thermonuclear bombs, they use fusion. And the fission bomb provides the energy for the fusion reaction. So this is one of the few ways currently that we can use fusion for anything. We have not been able to figure out how to use fusion for electrical generation. We want to, but we're working on it. You know, we're not close. We're not close at all. It's going to take a long time to figure out how to use nuclear fusion to generate electricity. But fusion is used in the sun, and we hope to one day harness that. So how does the sun work? Well, 4 protons come together. Actually, the sun is a carbon-12 star, so carbon-12 is used as a nuclear catalyst. That's kind of above and beyond this class, but it's kind of like this, but not exactly. There's carbon-12 is also involved, and it forms helium and 2 positrons. And as the star ages, there are other reactions that are going to happen. So what happens, the sun is going to burn for about another 5 to 10 billion years, in that range, when the hydrogen is going to get hotter and hotter and hotter. And then eventually the sun's going to start to shrink, and then it's going to be able to start generating carbon-12 from helium. And when that happens, the sun's going to get hotter, and it's going to expand. It's going to engulf Mercury and Venus and maybe the Earth, but the Earth won't be habitable at this point in time. The sun is too small to explode. If there's a star about 3 times as massive as the sun, it can start forming iron. Now the problem with iron is that when it undergoes nuclear fusion, it's endothermic, it absorbs heat. And so what happens is that the iron, as it's fusing, will get smaller, and then when things shrink, it'll get smaller and smaller and smaller, and then it'll implode. The implosion of the core of the star causes an explosion, which causes a type 2a supernova. And any element heavier, higher than iron, number 26, has been made in a supernova event of a star. And most of the atoms in our bodies, with the exception of hydrogen, is stardust. So we're all made of stars. And let's talk about the hydrogen bomb. These, nowadays, we have lithium deuteride in them and tritium. And they're set off, and there are other reactions going on which increase their yield. Yield means energy. And dirty bombs, what are dirty bombs? These do not have nuclear reactions associated with them. They have something else. They have like medical waste. They'll take the technetium or chromium from a hospital and put it on a stick of dynamite. So these are terror weapons. They're not designed to really do that much damage, but they're used to induce terror. So here in Hawaii, can you imagine what would happen if a dirty bomb went off in Waikiki? There would be a lot of terror, a lot of mayhem, and it would do a lot of economic damage. So dirty bombs are not very good strategic weapons, but they're good for terror weapons. Humans are actually fairly versatile radiation. we ourselves are slightly radioactive. And how does radiation harm things? Well, it's ionizing radiation. It breaks chemical bonds. Breaking chemical bonds, and then the issue is, are too many chemical bonds broken such that our body cannot repair them, or it's repaired incorrectly. And too much radiation can cause adverse effects. There's the long-term things like cancer, but there are acute effects too, short-term. So I told you before, beta radiation gets your eyes. A sunburn. A sunburn is a radiation burn. I get them all the time. I try not to, but I'm just so fair, I can't help it. I put sunscreen on very, very religiously. And the majority of the radiation we receive is natural, but if we get too many of them, radiation, I'm not going to tell you radiation is safe. It's not. It can be very dangerous, but it just depends on how much you get. And majority of it is from natural sources, radon gas. So here in Hawaii, the radon level is really low. So actually, the background radiation in Hawaii is pretty low. And I got emails from people around the country after the Fukushima event happened, and I remember this one gentleman in Chicago who was worried about coming to Hawaii, and he wondered why there was more radiation in Chicago than there was in Hawaii, and we're closer to Japan. And the reason being is because there's not very much radon in our soil. There's a little bit, but not very much, not compared to the Midwest in the United States of America. So here in Hawaii, we're going to have less of that. We get some from space, we get some from inside our body, and some in rocks and soil, even less so in Hawaii because we're not very radioactive here. Then, I mean, some people get a lot of x-rays, some people don't. I got a CT scan once, and that was 400 millirem or 0.4 rem. You're allowed to have 5 rem per year. And so I had a little bit of a higher dosage that year. But chest x-rays, dental x-rays, they're relatively minor. Nuclear medicine, like bone scans, we talk about that. And there's radiation and various other things. But you can see that the vast majority of our radiation exposure is natural. But the thing to watch out for is when there is a large release of radiation. So after the nuclear events at Fukushima and Chernobyl, the individuals close to the situations, they were in danger. And but us, so even me sitting in Hawaii and Fukushima, well, I was in no danger from that situation. But in general, radiation is not really something to be scared about unless you are around a nuclear reactor that is malfunctioning and or a nuclear blast. If you have any questions, please feel free to ask me. I know quite a bit about this subject because I entered grad school as a nuclear physicist and I switched to chemistry, so I'm very familiar with this.